Yes! Yeah! This whole time, I was just building suspense. I was just getting everyone excited for the last presentation. Anyway, I'm stressed now, but it's good. So I'm going to talk about why other things are broken today. So a very appropriate talk that we have. Very nice, light topic to finish the day with. But I want to talk about why I believe the internet is insecure, some evidence to support that, and I will spend a little bit of time thinking about how we can fix it, but it's more of a rhetorical question, so if you have any ideas at the end of the presentation, we can discuss. But basically, the overview of the presentation is, I'm going to look at the evolution, how it was born and kind of why it morphed into something insecure, and then we're going to take a dive into how we can hack certain elements of our software supply chain, and why having everything online and relying on the internet so much is causing a massive security problem. So let's get into it. So a brief history of the internet. So it was created around about 1965, but it took 4 years to send the first message from when it was created. So it took quite a long time in conception. It was really an academic project. And then it was used by various different people, but until 1990 when HTML was invented, then all of a sudden we discovered this marketable use for it. We had started thinking of how we can actually engage the regular public with the internet. HTML really helped with that because it made it accessible and it made it pretty. Although if you look at 1991 internet, I don't know if pretty is what you'd call it. But then it kind of went mainstream a year later. 4 years after that, we started looking at what we'd call now our first web apps. These are things that aren't just kind of dishing out information, not just readable sites. We're talking about systems that have back-end processes, systems where you can interact with, and that's really when we started to kind of birth what we call web apps. And web apps now has kind of almost encompass pretty much everything that we're building. Now, lots happened between 1994 2008, lots of companies, but in 2008 something interesting happened because we saw a shift again in what we thought the internet could be used for. This is the year that Dell first tried to trademark the term cloud computing. Now, they failed, but this was when we started to think of the internet as not so much just something we can access on our computers, but it can kind of morph into a computer. And then now we have about 5 billion internet users, and everything's kind of gone online. When we're building applications now, they're usually web applications. Things that even 10 years ago we didn't think we'd be able to do in a browser, we can do. We can edit videos in browsers now. All these intense applications have gone online. But when we look at the first portion of the internet, this is when all the kind of security was created. Asynchronous encryption enables us to send information back and forth. That was creating during this kind of incubation stage of the internet. And with the exception of kind of blockchain, we haven't really created much new security. We've improved on these concepts that were created around there, but the fundamental architecture that builds the internet has remained the same. But you could never have imagined, even if you were the leading visionary on internet technology in 1969, that it would turn into what it has today. So, the cloud. So the cloud, this term that was coined in 2008, it's a really interesting concept because it enables us to have a shift in our mind about moving everything online. But the reality is that it doesn't actually exist. It's something we've completely made up, and we've made up the cloud and other stuff because it makes us feel better about really the state that we're in. I'll give you an example. So Lucky Strikes, cigarette company in 1960. I don't know, what does this have to do with the internet? Well, and clouds. They came up with this slogan saying, "It's toasted." This was right after a report that definitively proved what they already knew, and that smoking was poisonous. So how do we rebrand something that's poisonous and make it sexy? You use the slogan, "It's toasted," right? It kind of sends this idea that it's safe, this idea that, oh, it's fine because it's toasted. Everything else is poisonous, but this is fine because it's toasted. But nothing actually changed. It was always toasted, and all their competitors are using toasted as well. This was a scene that was kind of made famous recently in Mad Men. If you watch that show, where they kind of go through how they created, that slogan. And it's what we do as humans is we kind of accept stuff that's different if we can obfuscate it enough to get it out of our mind. So in 2007, before cloud computing, before Dell kind of came up with this term, it was used a little bit before that, but this is what a server room looked like in 2007. This is where the internet was kind of hosted, the applications. Now, after 2007 and 2008, after cloud computing, this is what it looked like. It's exactly the same, right? But we call it the cloud. Oh no. Yes. Oh no. Oh man. So, this is the concept. Why do we call it the cloud? What has it done? I'm going to stop moving so much. It's because it takes away a level of control that we willingly give up because we believe that the cloud is secure. And we've done this, we've had all elements of software development now, where we've given up the burden of controlling something because we think that that's more secure, but we've kind of lost contact of what it all is. And this will kind of bring into what I'm going to talk about. Why does this matter? Why does it matter that the cloud isn't really real? And it matters because we're not actually comprehending what we've created, and we're not figuring out ways that we can actually, in real terms, fix it, because no one wants to actually talk about what it is. The cloud is someone else's computer. But it sounds so much better if I say that my data is hosted in the cloud than I say my data is hosted on someone else's computer. That doesn't sound very nice. But our applications also use the cloud now. Everything we do is in this cloud. And so we're going to look at kind of the modern software development lifecycle. What it looks like when we build applications today, how we rely heavily on these different components, third-party applications, how we host everything in the cloud, which basically just means it's remotely accessible, right? Doesn't matter if it's your computer or someone else's computer. If it's remotely accessible, you could argue that it's the cloud. And then how we can attack each point of these. Now, every single point of this, now this is a simplified kind of software development lifecycle, but it's generally agreed that these are kind of some of the components we have now. We have our software dependencies. These can be open source, but also third-party dependencies. We have our source code. Then we kind of go into these testing tools where we build and kind of test our applications. We deploy them. We host them on the cloud. And then we have our application. This is kind of the process that we go through to get here nowadays. And all of this is now in the cloud. Our dependencies are hosted and maintained, or they might be third-party service providers. It's in the cloud. Our source code is hosted in the cloud. Our testing tools are run in the cloud. We deploy everything into the cloud. The cloud is the cloud, and our application is in the cloud. So everything's kind of in the cloud, and this really has made things insecure. Now, when I talk about all these steps, I'm not really arguing against them, because I like everything. I'm just saying that we've made it insecure, and we need to start talking about the fact that it is insecure before we can start fixing it. So I'm going to focus on these first three areas because it will take me too long to kind of go through everything. But I want to use examples of real-life breaches that show definitively how each area of these are attacked today in modern kind of applications and with modern adversaries. We'll look at them and kind of show exactly what happens. So let's start with software dependencies. So if you're not familiar, what are software dependencies? So we have our application, and then we have these open source dependencies. So open source dependencies are pretty much little projects that do specific jobs that the community maintains, that's out there, it's free, anyone can use it. I used to be an architect, like a building architect, and we had the opposite of open source. If I did something really insignificant for a building, like a downpipe drainage detail, no one cares. When I did that, the client actually owned that detail. So even though I did it, not only could no one else use it, I couldn't even use it on my next project. Open source is the opposite, right? You do something that the community is going to find useful. It doesn't provide any real significant value to you monetarily, so you open source it. And this has happened and allows us to travel at much faster speeds. And this is a good thing. But we also have to realize that our dependencies have dependencies, and their dependencies have dependencies. So we end up, now this can go back and be extrapolated to multiple layers. You can go on to like NPM and look at all the dependencies, and you can generally get to about 30 layers. So this just means that even if you are not aware of what's in your project, that they are there. And then we have our third-party service dependencies. So one thing about moving onto the cloud and moving online is that we can now use services because we have the fundamental kind of objective or the fact that people are using our services online. So we don't need to kind of build authentication anymore. We can use Okta and we can communicate via their API. So these are it. For the first part, I'm just going to talk about open source dependencies, and I'll get to third-party dependencies later. Now, this is a really pretty illustration of how it makes sense, right? Your application's here. We have our first layer of dependencies, our second layer of dependencies, but it's not really realistic. This is a much more realistic view of what actually happens because our dependencies can be dependent on each other, and our third-party services have dependencies. And so looking at this and trying to figure out when something like log4j happens, which is one of these boxes down here, how do we know if we have exposure to it? So let's say that it turns malicious, or there's a vulnerability in there, we all need to fix it. And then all these things that are connected to it also turn malicious, which really affects our application, but we don't even know what's in our software anymore. In fact, 95% of the code isn't our own code. It comes from dependencies. Right? And that makes sense when you think about it. If you're going to build a social application, is it how your users log on to your application that will make the difference? Maybe, but it's probably going to be your algorithms. And then you can just take everything that's not really specific to you, and you can just use other services and dependencies. So that makes sense. And what's scary is that we trust this code more than we trust our own code, even though we don't know. And that is because it's toasted. Right? It's, you know, like it's got that layer of obfuscation. So let's have a look at an actual example of when something was attacked. So there's lots, I can go on lots of examples. I've tried to stick with just one, but yeah, we'll see. So here we are, UA parser. So this is a JavaScript for Node. It's a dependency. What it does is that it detects what browser, what machine, basically information about the machine that you're using. So if I'm on a Mac, then this will let that person know. It does a very specific job. It's not that important, but you can understand why this is an open source dependency. Lots of people will want to do that. They don't want to write it themselves. So when we're choosing a dependency, there's a lot of things that we will do, right? We're not silly. We're not going to pick some random project that's out there on the internet. So there's certain levels of trust that we will go through to do this. First level of trust, this has 10 million weekly downloads. All right, lots of eyes on here, probably not malicious. Like, passes that check. It's got 56 versions, so you could go onto GitHub and look at it. This one's been maintained for over 5 years, so it's got a good track record of maintenance. Another tick. And 1,600 other dependencies use this. So another tick. I would look at this, and being the most skeptical person, which I probably am, like I would pick this. I have no problem using this dependency. All right, so we have a look at who created this dependency. We like this guy. This is Fazal. Fazal's a good guy. He's the maintainer of this. So we like him. He didn't do anything wrong, but he's been managing this dependency for a while, and it's used by millions and millions of apps, and even the apps that don't use it, it's got over 1,600 dependents, so you've probably got exposure to this. And then this happened. On a Russian hacker forum, some guy said, hey, I have a really popular account. There's no two-factor authentication on this account. It's got 7 million installations weekly. and it will be suitable for these malicious activities. Give me lots of money and I'll give you access to this account. So you've probably figured out whose account this is. So essentially, you've done nothing wrong by choosing to use this dependency. The maintainer may have been phished, may have had their credentials stolen some other way. We don't really know. It's not really their fault, but if their account's been compromised. Then what happened is they injected some malicious code into this project, and then the rest happened. That project was turned malicious, millions of websites. What they did is they had a credential stealer and a crypto miner built into there that millions and millions and millions of websites were using. Even if this only stayed online for a couple of days and it stayed online for lots longer than that, then you've still got so much information that you can do malicious activity with if you're stealing credentials, that that's going to keep you busy at least until Christmas. And then so he reached out, he got back control of the account, they marked the package as malicious, but most people probably don't even know that they were exposed to it because it's so far down the line of dependencies, and there will still be people that are running this malicious package today, I can almost guarantee it, even though we know about it. So this is just kind of one area of how our open source dependencies can be compromised. I have one other quick one, but I'll try and go through it quickly. But this is Event Stream, another really popular one. What have we got? 3 million weekly downloads. Does another kind of specific thing in JavaScript. So what happened here? Well, the guy that ran Event Stream got kind of bored of it. It wasn't really perfect for him. He couldn't maintain it. But then a really helpful person came along and said, hey, I'll help you maintain this open source tool. And he did a great job. He was very helpful. And then eventually he took ownership of the project. And then, to stay under the radar, he introduced another dependency called flatmap stream. That was malicious. And this whole process that he did was just to turn event stream malicious. And he had made flatmap stream to look very inconspicuous. You wouldn't have known much different unless you were really, really going into it from event stream because it just added in a dependency, not a big deal. But event stream was turned malicious. Millions of websites suffered because of it. So this is why we need to be really careful with our dependencies, because we always just think that it's secure, it has the power, but these are just people that are running behind it. It's not insecure everything in the cloud. So the next that I want to talk about is source code. So source code is a huge component to everything now. So I want to talk about how our source code can work against us and turn malicious. So source code is everywhere. And even if it's private, it's sprawled out into lots and lots of different places. And source code can contain lots of sensitive information that attackers can use, and I'll talk about that. So you probably know this website. This is GitHub. So GitHub is most known for its open source kind of code sharing. A lot of the dependencies we just talked about would be kind of in here. Companies also use it. It's really popular. Over a billion commits are made publicly on GitHub every single year. So really, really popular. Now we understand that things on the internet, when they're public, it means that anyone can access them. But often what we don't understand is public means broadcast. So this is GitHub API. You can access this with no authentication. If you go to api.github.com/events, you'll get a list of all the activity that's coming on publicly. And then you can use these here. These are kind of the core ones that I would use to kind of monitor this activity. So just remember that, because I'm going to come back to this in a minute. But public doesn't mean someone can access it. Public generally means broadcast. And this is because of how we use APIs and everything. Now, bad guys can monitor this, and I'll refer to some research in a minute. But I also want to talk about, you're probably thinking, aha, but my code isn't public. I have closed-sourced code, so therefore I got nothing to worry about with source code. That is not true. So there's a couple of ways that source code can become public. So if you have your own code repositories, you're hosting it yourself, research by Cyber News just recently found where they did some kind of random scanning of IP addresses. They found 2 million accidentally exposed Git repositories. So this means that you've got private source code hosted on your application, but it's actually remotely accessible by everyone, right? That's because you've put your source code into the cloud, you haven't configured it correctly, it's toasted, but actually it's completely accessible to everyone. So your private source code isn't private at all, and I'll talk about how attackers use this to exploit it in a little bit. But code is also incredibly leaky. That's its nature. Once it hits version control systems, Git, usually hosted kind of remotely in the cloud, it will then get cloned onto your developers' machines. It'll be shared in messaging systems. It'll be in our running applications. It'll be in our Docker images. So if code enters into our Git repositories, we have no control over ultimately where it ends up. And this slide we saw before, I want to talk now about these third-party services and how we can attack them kind of using the sprawling nature of source code. So unlike dependencies, these are kind of separate companies, separate services, and our application needs to communicate with them, right? So if we're using Stripe to process our credit cards, our application first has to authenticate, get approval to do that job, and we do this using secrets. So the secret is just a really long password, but the key is that it's made to be used programmatically. These aren't meant to be used by humans, they're meant to be used by our machines. Our application uses this to communicate to Stripe and authenticate ourselves, and then we can do the stuff. Now, these are the crown jewels of any organization. If an attacker gets these, and they're always after these, they can properly authenticate themselves into services. It makes them really hard to detect because they're correctly authenticated. And these secrets are absolutely everywhere. So secrets are API keys, they're credentials, they're certificates, and what's important is that they often end up in source code. Now, they're not actually meant to be in source code, but they're there pretty much always. In every case, you'll find secrets buried in it. There's a couple of reasons for that. But because secrets are made to be used programmatically, if I'm a developer, if I'm quickly trying to get something to work, I can just hard code that secret into my source code, test that it's working, and I can delete that later if I want to. And we use these secrets for absolutely everything, for different things, for managed databases. So these can really grant access to everything. And when we're talking about source code, if we look at our kind of Git tree, if we're developing something, if I'm doing something on a development branch, if you're not familiar with kind of Git and what this all is, then if I'm just kind of working separately from the main product, I'm working on a little project and it's kind of being kept separately for the moment. So I can hard code a credential, hard code an API key just to get something working. I can remove that later. And then when we do our code review, we're kind of making this, we're going to look at the last two commits. So we're not going to see any secrets in here, even though they're there. And we have to remember that everything that we do in source code lives on in our history. If you delete something, it's still there in the history. Okay, so I'll try and pull all this together, lots of information. But going back to GitHub, right? 1 billion commits were made on GitHub last year, lots of open source. Now we have these pesky things called secrets. Apparently they're in our source code. So what we did is we decided to scan GitHub for an entire year to see how many secrets we could find. So 56 million people pushed or uploaded code to GitHub in 2021 throughout that whole year. And we found 6 million credentials. 6 million credentials to all kinds of things. This is a huge problem. So when I said that we've moved everything to the cloud, now you have access to everything, just on publicly available code that's broadcast through GitHub. This occurs because we're relying so much on these third-party applications, and we're not understanding the severity of kind of what we're really doing. If we look at the types of secrets that we found, so data storage was about 21%. Cloud providers, so we found over 1 million credentials to cloud provider accounts like AWS, GCP. So you don't need to be very imaginative to know what you can do if you have access to one of these, right? You can shut down services, you can access data, maybe you can create accounts to hide yourself. So we're finding lots and lots of sensitive information out in the public sphere. And if you're a developer, you might find this funny, because I did, but we found 500 commit messages where the commit message was your GitHub access token. So this is like having an email and then putting the password in the subject line and sending it out. This is exactly what this is. So this is kind of like just not understanding technology and not understanding like just how broadcast everything is. So there's a lot of access that you can find out there. And so when you're also talking about like private accounts, you could have your code locked behind the tightest authentication, but if one of your developers does this, then someone has access to it. All right, so let's talk about some breaches now. So we know that this is bad, but do adversaries know this? Do we have examples of when this has happened in the wild? We have lots of examples. I'll try and keep it one. This isn't formatted very well, but we'll figure it out. But we know SolarWinds probably. Big supply chain attack that happened a while ago, granted access to inside into government organizations and everything. So this was a really massive, massive breach. How did this happen? So here, you can't see very well, is code that was on GitHub.com. A SolarWinds employee accidentally published code on their personal public GitHub account that contained access to SolarWinds' FTP update server. Now, SolarWinds haven't said that this was the initial point of access, and it was a very sophisticated attack, so it's likely that there was multiple elements to it. But what we do know is that threat actors got access to the FTP server account. They were able to inject a malicious package. That package was downloaded, and then everyone using SolarWinds was then breached. So this here is just kind of showing when we put everything up into the cloud, it becomes accessible so easily, and it takes small misconfigurations, small mistakes, for us to accidentally expose our secrets. And then kind of the whole show comes down. And this was a worst case scenario for a lot of people because SolarWinds had admin access to all these networks. So once they were in there, they were really able to do kind of anything they wanted. This was the guy that ultimately found it and reported it to SolarWinds, and they kind of removed it. And this was before the breach happened. So hopefully they did remove it, and this wasn't actually how the attackers got in, but it's an awfully big coincidence because it happened in the same month. And I now want to talk about attacks accessing private repositories. So again, sorry about the formatting, but we've seen a lot of headlines, particularly this year, about large companies having their private source code accessed, right? Microsoft, NVIDIA, the Lapsus group went on a rampage at the start of the year, publishing everything. And then you can think to yourself, like, how do these great organizations have their code kind of involuntarily open sourced, let's call it. And it's so easy to make a mistake with private accounts, and it's so easy to gain access to them that it really happens everywhere. In fact, on average, in a typical company with around about 400 developers, we'll find about 1,000 secrets inside private source code repositories because private source code is toasted, meaning that it's kind of behind an authentication layer, and we don't understand kind of how easy it is to get past those. So let's talk about Twitch. So last year, Twitch's source code was leaked publicly, and Twitch kind of kept it under the radar, or at least they didn't want to make a big deal about it, but we actually scanned this source code and we found over 6,000 secrets inside them. That was all public. So there was 194 AWS keys, 69 Twilio keys, 4 Stripe keys, so access to payment systems, inside their source code that was now public. So how did this happen? Well, at the start, I said that there was 2 million Git accounts that were, when they scanned them, were found to have remote access, were found to be kind of not behind authentication layers. Well, Twitch was one of them. So Twitch had a self-hosted Git server that was remotely accessible, and even though you would need a little bit of knowledge to be able to scan an IP to try and find the Git server, there's tools that can do that for you quite easily. And so here we have an instance where the source code is all hosted in the cloud, and that cloud is misconfigured. Really easy to do this misconfiguration, especially if it's kind of managed by YAML files and you just kind of forget to put that in. And then kind of everything gets exposed. All right, I'll quickly move on to kind of my last area of talking about the software and how we can attack it. And now I want to talk about attacking the testing tools. So testing tools kind of sit in your CI/CD pipeline. If you're not familiar with what that is, it's continuous integration, continuous deployment. When I publish new code, it can automatically be tested to check that it's working correctly. And so this has kind of become a really big part of our process because it enables us to move quickly because we don't need to manually test things anymore. We can automatically test our code and applications. All right, so like GitHub, there's another site that hosts a lot of information. That's Docker Hub. So Docker Hub is the largest repository host for Docker images. Docker image is just like a package, a collection of everything that an application needs to run. There's 8 million Docker images on Docker Hub. We scanned them to find any secrets, and we found about nearly 5% of Docker images contain at least one hard-coded credential, one hard-coded secret that can give access to that. So that's huge. So pretty much 5% of what we use on Docker Hub is insecure. And it's not just kind of small, personal projects. We find this in really large kind of accounts and really popular Docker images. So I'll do a breakdown of an attack on a testing tool that used Docker images to do it. So CodeCov was an attack that happened last year. CodeCov is a testing tool. It is a code coverage testing tool. So it tests how much of your application is being tested. It does a very specific thing. It's not something that has critical access to anything. It's not something that you would put lots of kind of authentication and control over. But it's a very helpful tool. It's a great tool. I personally still use it. So what actually happened? So in early January, the latest version of that Docker, the Docker image contained a plain text credential. That credential granted an attacker access to a cloud drive, which contained a bash uploader script, and then they were able to edit it. Basically, it contained access to an element of that application. They were able to inject malicious code into that. And then the exploit happened, and every single person that used CodeCov had all their secrets sent to the attacker. So when CodeCov tests an application, when your application is being tested, it needs to be built. In order to build your application, you need access to your database, to the third-party tools. So in your environment, you have all your secrets. Now, hopefully, you have development secrets and not kind of production secrets, but often not the case. But even still, there'll be some secrets in there that are useful. For instance, your access to your private code repositories. So at the time, CodeCov had 20,000 users. Some of those users were Rapid7, a massive security company, Twilio, Monday.com, HashiCorp, another massive security company. And these companies were all breached because of CodeCov. So what happened is the attacker updated this bash uploader script, and then every time Rapid7 or every time HashiCorp retested their code, which was probably multiple times a day, all their credentials were sent to the attacker. The attacker then gained access to their private source code, and they found more credentials. The one that I find, by the way, it was just one line of code. This is the bash uploader script. This is the line of code. It would have been really easy to miss this. But the one I find really funny is that HashiCorp had credentials exposed. HashiCorp is a security company that's whole product is designed around about not exposing your secrets. There's a secret manager. Inside their source code were secrets. So it's not that HashiCorp is a bad company, it's just that this is really the state of every company. And if HashiCorp has secrets in their code repositories, then we all do. And we can all use that. And because everything is online, and because of how we build our applications, is that everything is kind of so easily attackable with just the smallest of mistakes. Okay, so I'll start to kind of wind up and just do a bit of a recap. So we have the software development lifecycle of our modern applications. So we talked about dependencies. We talked that dependencies can be turned malicious by either taking over from accounts or injecting malicious code, but these are maintained by the community. And because it's all kind of automatically done, and because we trust it, because it's in the cloud, and because we just assume that everything is secure, then when these get turned malicious, they can have huge impacts, often go unnoticed. Our source code contains huge amounts of sensitive information, like secrets, but there's also other elements in source code that we can use. I have another talk called Hacking Code, where I go into that, but I won't go into it here. But our source code is mainly hosted online because people need to have remote access to it. It's hosted in the cloud, let's say. Now, because of that, it takes a small misconfigure error or an error from your user to accidentally add something to a public repository that's not meant to be there, for all of that to be exposed. And then once an attacker has those credentials, then they can conduct an attack, get into different systems and move laterally. We've talked about testing tools. So basically, testing tools have access to huge amounts of sensitive information. Attackers know this, and there's lots and lots of tools that sit in there. And because of that, they're a huge target, and it's easy to turn something malicious that has a huge effect. When you compromise one of these, it's not just that you're compromising the application that's using it, it's that you're compromising everything. There's millions of applications that may be affected from that have a huge follow-on effect. So ultimately, it just takes one dependency to be turned malicious for just about all the websites and applications on the world and all of our data and everything that's toasted in the cloud to become accessible. And this happened, right? This happened with log4j. Now, it didn't happen that a malicious user found the vulnerability of log4j. It's a logging program for JavaScript applications, did something really boring, right? No one cared about it, but it was important for Java applications. And that wasn't turned malicious, it was found to have a vulnerability in it. And then basically, we started scrambling to try and figure out what was dependent on that. And even if you weren't using log4j, there was probably a dependency, there was probably a testing tool, there was probably some cloud source code coverage, there was probably a third-party application that was. So you had exposure to it. So the whole internet, for like a month, was totally vulnerable. And not only did we know about it, there was also like descriptions of how to exploit it. So now luckily, like the worst case scenario, there's lots of attacks that happened because of that. Lots of bug bounty guys got lots of money because of that. But this is really kind of the fragile state that we've built the world on. So we're all screwed. All right, so I'll kind of talk a little bit about why I believe the internet, how we've built it, how we're kind of maintaining it and building web applications is fundamentally kind of flawed because we have inherent trust of things, because we have too much access. So let's talk about what we can do to prevent this. The first thing is to talk about what you can do. So if you're a developer, if you work for an organization, there are things that you can do to limit your risk. Not eliminate it because it's a problem of the architecture, in my opinion, but there are things that you can do to at least limit what your potential exposure could be. So the first thing is you need to assume that you'll be breached, right? You need to assume that your dependencies will be turned malicious. If you adopt this posture, then you can start segmenting things, and then you can start acting in a way that will mean that your security posture will change. You know that your source code may be accessed, then you're going to change what you're going to put in there and how you're going to monitor it. So the first step is just to assume that you will be breached and understand the implications of that and try and limit that by segmenting different components and different elements. So there's tools that we can use, especially for dependencies. So SCA, software composition analysis tools, Mend, Checkmark. I think Mend and Checkmark is the same company now. Sneak is another one. And these basically analyze our dependencies, and if there's vulnerabilities in them, it will let you know. So this is kind of something that everyone should be doing, right? We should be using these tools to discover if our dependencies are vulnerable, and it also helps us understand how our software is put together. And if we have a dependent of a dependent of a dependent of a dependent of a dependency, then that is malicious, that we can find out about that and understand our exposure. We need to implement a concept called zero trust. So zero trust is basically just not believing someone because they have an API key. If I come to you with an API key to access something, then I should be from a whitelisted IP address. I should be from a known service. So we need to add additional layers of security so that we don't just inherently trust anything that's out there in the cloud. And other areas of zero trust, like using short-lived credentials, making sure things just don't last forever, is important. Get rid of your secrets in your environment. GitGuardian is a great tool for this. I work for GitGuardian. They're paying me to be here. Help me out. Download it. No. We're totally secure. No. Sounds like we're not. But anyway, identify where you are, where your secrets are in your networks. Identify if they're in your source code. Identify if they're in other areas, because you'll be surprised. Particularly with source code and its history, there's going to be stuff that people have done a year ago that's still going to pose a risk for you. And unlike all other vulnerabilities, which expose themselves at like the runtime, at the last kind of part of your deploying your application, if you have a cross-site scripting vulnerability, you fix it and deploy a new application, you no longer have a cross-site scripting vulnerability. If secrets are in your history, it doesn't matter if you delete them, they're still there, people can still find them. And segment your development environments, including secrets. So segment out your development secrets from your production secrets, and segment your environment so that people can't leapfrog and move laterally between them. Okay, getting to the end. What can we do now? And so this is kind of like, what can we do holistically to try and eliminate these problems? So here, if you have any ideas to add, please. These are some of mine. Some of them are happening, some of them aren't. In my opinion, we need to move away from secrets, because that is a weak point in just about every attack. It may not be the initial access point, but it's a point where you can elevate privileges. So we can do this with some concepts that we're already kind of coming out, like dynamic secrets, secrets that are created and destroyed immediately, using centralized trust for these systems to try and eliminate the need of this kind of point of weakness. We need to start understanding much better our software composition, so that when things like Log4j or FlatMap, event stream happen, we understand what our exposure is to it and if we do it. So SBOM is something that was in the White House cybersecurity, a paper that happened earlier this year, software bill of materials, something that companies need to have now. And this is kind of a good start into making everyone understand what's actually in our software. What is the 95% of our source code that we're not actually using? What are the third-party applications that we're dependent on? Infrastructure as a code, IAC, is kind of this concept that we can write code to create infrastructure. It's great. I like it. But basically, I don't understand why. The default of it is always to be insecure. Like, you have to make an active effort to make something secure. But by default, it's not. So we need to kind of change that so that it should be hard to make a Git repository publicly accessible on your server. It shouldn't be the default of having to know not to do that. We need platforms to normalize security. We saw that one of the dependencies was compromised because the guy didn't have multi-factor authentication. And we need to normalize things like this, and the platforms that host our dependencies need to implement this and force security on us, because if you're anything like me, you're lazy. I hate multi-factor authentication, but oh my God, it saved my life a couple of times. So it's great. And security training needs to be a pillar of developer training. I was a founder of a startup, still exists today, and I kind of wasn't until I got to my security journey that I realized how incredibly insecure our whole systems were. And it just is not prioritized over speed. Speed is the number one threat. That's what I think we should be doing. So that's all that I had today. If you want to find out more, here's a QR code to some report. This is the state of secret sprawl. I mentioned some of the numbers there. You can download that and read more. I know for the technical problems at the start, I apologize, but we went a little bit over. I tried to make up some time. But I will be happy to take any questions as long as they're easy now.